I'm Ethan. I'm an educator here for the Cheehaw Park and Zoo, the Flint River Aquarium, and the Throne-Atiska Heritage Center, which is the Artesian Alliance here in Albany, Georgia. And today I'm going to talk to you about extinction and fossils and all of that sort of stuff. So this is a subject very near and dear to my heart because I am a geologist, and a geologist studies rocks. And part of rocks is fossils. So we're going to look at fossils and extinction and how extinction has actually, it's not really an end-all, be-all extinction. It drives, it's more like a cycle. It drives evolution and adaptations for life. So to start, let's talk about evolution. Now, whenever I say evolution, I know it's kind of a hot trigger word. A lot of people get really opinionated about what evolution is, but whenever I'm talking about evolution, I am simply talking about species changing over time. So whenever a species changes into to develop something new, that's what I mean whenever I say evolution. So this guy named Alfred Russel Wallace and Charles Darwin, they both published a book entitled On the Origin of Species in 1859. And that book described the theory of evolution by natural selection. So natural selection means that there are different pressures in our ecosystem. So different things pressure animals to behave in different ways and to evolve in different ways. So the example that Charles Darwin gave was finches. He saw different finches on different islands. And finches, they're a type of bird. They're a small little bird. He observed that on the different islands in the Galapagos island chain, the finches had different kinds of beaks. And he realized that the finches with broader beaks, they had these broad beaks to crack open nuts and things. And the finches with really small beaks, they had those beaks to get at berries inside of thorn bushes and things like that. And then there were, so on islands with only thorn bushes, you'd never find a broad-beaked finch. You'd only find the finches with the very narrow beaks, because the broad-beaked finches wouldn't be able to get at those berries. So the narrow-beaked finches got to them instead. And on islands with no berry bushes, with just broad-beaked finches, there were only nuts and stuff. There were no berries. So the finches, he concluded that the finches had to have evolved to be the way that they are. So if you've got a finch with a really narrow beak, then that means that there was something in the environment around it that made it develop that really narrow beak, right? In this case, the thing that made it develop that very narrow beak was the fact that there were berries in thorn bushes. So in order to get around the thorns and get at the berries, they had to get really long, slender beaks to be able to grab them real quick, right? So there are different pressures in our environment around us that force animals to sort of change and develop and evolve. That's what evolution is. Like I said, his example was finches. There's also the Galapagos tortoise, which he observed. The Galapagos tortoise is that tortoise with a really tall neck. The reason why they have really long necks compared to other tortoises is because they eat branches. So they like to reach up high to grab branches and stuff. So the tortoise just slowly got a longer and longer neck to be able to reach those branches. And eventually they evolved into what we know as the Galapagos tortoise today. Now, what's kind of weird, I think at least, what's kind of weird about the theory of evolution by natural selection is that it was inspired by economics. So what does money have to do with finches? Well, in 1797, a man named Thomas Malthus published a book called Principle of Population. And this book is kind of controversial. It's not exactly correct, but it inspired this way of thinking that still sort of sticks around today. It's the idea that whenever populations, and he was talking about human populations in this case, whenever they grow, they'll grow and grow and grow until all of the resources are consumed. And then whenever they run out of resources, the population is just going to crash again. And he had this idea of catastrophe. And it's literally called catastrophism. That's this psychological theory. Now, Charles Darwin and Alfred Russel Wallace, whenever they published On the Origin of Species, they actually took inspiration from this idea. They concluded that if Malthus is right and human populations are affected by resource amounts and they grow in places with abundant resources and they don't grow in places with very little resources, then that must be true for animals as well. So they grow, animal populations change with resources. So this inspired the idea that evolution is fueled by catastrophe, because if it applies to human populations, why not apply it to animal populations as well? So this idea that huge catastrophic events caused the changes in our evolutionary line. So creatures didn't evolve unless there was some sort of major extinction event that drove them to evolve. The opposite idea is known as uniformitarianism, which is the idea that evolution is just very slow and gradual and changed by just very slow gradual changes. So catastrophism, evolution is fueled by very fast, quick, explosive change, and uniformitarianism is that evolution is fueled by very gradual change. So if you got nothing else out of the last few minutes here of talking, that is the most important 2 bits of information there. So which one is it? Which one actually fuels evolution and changes in species? The answer is both. Uniformitarianism is usually how species evolve. So very slow, gradual changes is usually how it goes. But there are also examples of extremely quick, catastrophic change, like the asteroid that wiped out the dinosaurs, for instance, that drove evolution in really quick spurts. So it's kind of both. So now we're going to talk about mass extinction itself. So whenever I say mass extinction, goodness, sorry, I was having some things. Whenever I say mass extinction, I am talking about a massive extinction. So like a very large chunk of all the life on the planet gets wiped out, usually over a very short period of time. Now, whenever I say short period of time, I mean geologically short. So like over the course of several million years. So if you were actually living in a mass extinction event, you might not notice that there's a mass extinction event going on because it happens over such a long period of time. But geologically speaking, it's a very short period of time. So the way that we can tell if mass extinctions occurred is if the fossil record suddenly changes. And so basically what happens is whenever you're looking at a wall of rock, there are these very fine points in the wall of rock where extinction events occurred, where you can see very clearly the fossils underneath look very different from the fossils above. And then usually the fossils above start out really small and then gradually get bigger. And that's because this rapid evolution of species occurs after mass extinction events. So there have been 5 mass extinction events in the last 550 million years, which is the last 550 million years is whenever we can really chart fossils well, because that was the point where we developed hard shells and things that actually fossilize. So there have been 5 major ones in the last 550 million years. And this chart below describes extinction from based on time. So this is percent of creatures that go extinct. And this is time. So it starts at 542 million years ago. So as you can see, there's a big spike here. There's another big spike here. There's one more big spike here, another one here, and another one here. And actually, it doesn't show it very well, but there's actually a growing spike right here in our modern day as well. So there are we're going to count both of these as 1, 2, 3, 4, 5 mass extinctions that we can observe. And you might recognize a few of them, believe it or not. So let's talk a little bit about geologic time for just a minute here. So whenever I say geologic time, I'm talking about the timeline of Earth's history. So 4.6 billion years ago, whenever the Earth formed, all the way to the modern day. And we usually split it into eons, eras, and periods. So it's like hours, minutes, and seconds, if that makes sense. There are different periods in each era. There are different eras in each eon. And each one is defined by what you can find. So different fossils. So like, for instance, the Mesozoic era here, right here, is the Triassic, Jurassic, and Cretaceous. And you might recognize that because that was the age of the dinosaurs. So the Mesozoic era is defined by having dinosaurs in it. The Cenozoic era, which is the one that we live in now, is defined by having a bunch of mammals in it. And the Paleozoic era is defined by being before dinosaurs developed. So each one is defined by what's in it. And we can actually get even more specific if we go into periods, but we're not going to get that specific today. But each one of these is defined by what fossils you can find inside of it. So extinction actually creates different time periods. So like, for instance, there was an extinction event right here between the Permian and the Triassic. There was an extinction event between the Triassic and the Jurassic. And there was an extinction event between the Mesozoic and the Cenozoic eras, which is right here. So there were 3 extinction events just right here in this short span of time. There was also an extinction event right here and an extinction event right here as well. So that's where our mass extinction events occur in our timeline here. So I actually this is another example of a geologic timeline. I made a short video highlighting geologic time by distance here. So it starts at 4,500 million years ago, so 4.5 billion years ago. And I just made a string. It just follows along, and it highlights a couple of the important events in our history. We're not going to talk about these events very specifically here, but this video does highlight just how long geologic time is. So what I did was I measured out a length of rope, and I made every centimeter 1,000,000 years on this rope. So as you can see, there's a whole lot of stuff. There's a whole lot of nothing happening right here, but eventually 1,500 million years ago, oxygen enters our atmosphere. And then we got to walk a little bit more here, but do you see how much walking there is just to follow this geologic time here? So this is whenever we see our first multicellular life. And then we get the Cambrian explosion and our first vertebrates. Vertebrates are creatures with backbones, so they're our earliest ancestors. And as you can see, we're moving pretty quickly here now. So here in just a moment, we're actually getting closer and closer to the end of time here. Well, the end of time is in the modern day. So here we go. And this is the part that I think is important for this. That's how far I had to walk. If every 1,000,000 years was 1 centimeter, 1 itty bitty little centimeter, I cover about half a football field trying to track all of geologic time. So these mass extinction events occurred over kind of broad periods of time. So now we're going to talk about the 5 mass extinction events, and then we're going to get into sort of what drove them and what caused them. So the first mass extinction event was the Ordovician-Silurian event. And the reason why it's called that is because it occurred between the Ordovician period and the Silurian period. So imagine an Earth 440 million years ago. Creatures were just starting to get onto land, but most animals lived in the water still. You had things like ancient squid, trilobites, lots of different kinds of coral and anemone, a whole bunch of very primitive water-dwelling creatures. So at this point in time, the Earth was fairly warm, and it was generating a lot of greenhouse gases. Now, greenhouse gases are things like carbon and stuff. And what it was doing was it was making its way into the air, and it was actually making it so that the sun couldn't reflect air or couldn't reflect its light as easily onto the Earth. And so slowly but surely, the sort of chemistry of the Earth started to get off balance, and like a top where it starts to wobble and wobble and wobble before it falls over, the Earth started to glaciate, so it started to freeze. We get what's known as a snowball Earth at this time. The entire Earth just kind of froze itself solid. Everything except for the very center of our equator was pretty much frozen solid. And 85% of all marine life died. It's a crazy amount. Tons of shelled creatures like clams and brachiopods and things like that just went extinct super quickly. After that, the population recovered for a while. So after the snowball Earth, the Earth kind of froze over, and then it slowly recovered and got back to sort of a state of normalcy here. And then about 376 to 360 million years ago, we have what's known as the late Devonian extinction event. So at this point, you had animals moving onto land. You had early amphibians living across land. You even get some very early precursors to mammals and dinosaurs and lizards and stuff around this time. 50%, about half of all the animals on the planet went extinct at this point. But what's interesting about this extinction event is very few land animals went extinct. So all of these lizards and amphibians and mammals and stuff that we have running around on land now, they didn't go extinct. Neither did any land plants. It really seems to be almost exclusively marine animals that went extinct at this time. And what's interesting about this one is we just don't know what caused it. So some people think that it was caused by a rapid cooling event, just like the last one, a sort of snowball Earth situation. Other people think that maybe an asteroid hit the planet. Still other people think that it was a chain of volcanoes that all erupted and caused it all. But this chart that I have here shows pretty clearly what happens during an extinction event. So do you see how many different kinds of creatures are here? And then, as you can see, the extinction starts to occur. And by the time we get into this area here, the extinction event is done. The mass extinction has already happened. And you see there's very few animals left compared to over there. So now we're going to get to the ones that I find the most interesting, the ones that involve dinosaurs. So the Permian-Triassic extinction event, aka the Great Dying. It started right whenever dinosaurs were starting to show up, so about 250 million years ago. It is the largest extinction event to have ever happened on the planet. 81% of all ocean life and 70% of all land life went extinct. It was caused by extreme amounts of greenhouse gases. So a lot of carbon dioxide in the air made everything heat up to the point where the oxygen started to disappear and all of the animals just died in incredible amounts. It's crazy to think about. So Pangea was a thing at this time. All of the continents were coming together. And this chart shows all of the creatures that went extinct versus all the creatures that survived. So as you can see, by the end, almost all creatures went extinct. And this shows from the North Pole to the tropics to the South Pole. So a couple more creatures survived in the tropical areas, but on the poles, almost all creatures went extinct. So you actually see the extinction of entire groups of animals, like trilobites and several other kinds of amphibian went extinct. And so many creatures went extinct during this one. But because there were so few animals left, it actually paved the way for creatures like dinosaurs to come about. So this guy actually isn't a dinosaur. He's a crocodilomorph, which is a fancy way of saying this is an ancestor to our modern day crocodiles. So right in the middle of the Mesozoic, you actually get what's known as the Triassic-Jurassic extinction event. 34% of all marine life went extinct at this point, but a lot of groups were unaffected, such as dinosaurs, which managed to really see a huge growth in the Jurassic after this. A lot of plant species, most mammals, and then flying lizards like pterosaurs also, so like the pterodactyl and things like that. And also most crocodiles and other reptiles managed to survive as well. So these two extinction events, the Great Dying and the Triassic-Jurassic extinction event, both sort of fueled the dinosaurs being able to rise up and take over, because now suddenly they're not competing with anything. There's barely anything left. It'd be like if you were trying to get on a sports team and half the team quit. Well, all of a sudden, you have way more opportunity to join the sports team. And that's kind of what dinosaurs did. And then finally we get to the one that everybody knows about, the most recent extinction event, the Cretaceous-Tertiary extinction event, or the KT extinction event. And this is the extinction of the dinosaurs. It's the massive impact from a meteor or a comet or something like that wiped out tons of animals. Almost all large animals died, with very few exceptions. Almost all creatures that weighed more than 25 kilograms, so like 50 to 60 pounds. Any animal that weighed more than that just died. So only small creatures were left. So early mammals, which were very small and very rat-like, small amphibians, small reptiles, and almost all dinosaurs went extinct, except for birds. Birds are the direct descendant of dinosaurs, so they did not go extinct. And so what we're looking at here is actually the Yucatan Peninsula in Mexico. We managed to figure out that the crater of the thing that impacted the Earth at that time is in the Yucatan Peninsula. It's right here. And the Yucatan Peninsula is in Mexico. You know, here's the Gulf Coast, and then here's the Yucatan Peninsula. It's that little part that juts up and out. And actually, the KT boundary, the extinction event, is really easy to spot. If you're ever somewhere where it's exposed to the surface, it's this dark, extremely noticeable black line that occurs. So it's very, very obvious, the KT boundary. And all large life went extinct at this point. So let's talk about what happens after a mass extinction now, because we've talked about the 5 big mass extinctions. So what usually happens after a mass extinction is you get this very rapid, suddenly all of these creatures that are left over suddenly just evolve in all kinds of different ways to fill these roles that used to be filled by larger creatures, because usually it's larger creatures that go extinct. So things like grazers and large marine mammals and predators and stuff like that, they get replaced. So what I have right here is actually this bottom one is a dolphin, and this top one is an ichthyosaur. An ichthyosaur existed 200 million years ago, and a dolphin exists in the modern day. A dolphin is a mammal, but this guy is, believe it or not, a lizard. This is a reptile. It's a type of reptile that's fairly closely related to lizards, but they look almost the same, and they filled almost the exact same role They were both large predators in the ocean. It's just kind of crazy to me. So you'll see this time and again whenever you're looking at fossils that existed at completely different times from one another that look very similar, because these catastrophes fuel evolution, and evolution likes to put you in the best position to survive. And so these creatures just constantly evolve into the same ecological roles. So now I'm going to talk about a couple examples of fossils and how they shed some light on extinction. So what I have here is an Archaeopteryx. An Archaeopteryx is this sort of missing link between dinosaurs and flying birds. So this guy was a lizard, and he was very similar to a dinosaur, but he had feathers, which you can see here. And so what this guy did was he lived in treetops, and he would hop from treetop to treetop, and he would use his feathers to sort of give him a little bit of gliding power. So he couldn't quite fly yet, but you can see that there was this pressure from living in the treetops. Living in the treetops means that it's advantageous for you to be able to glide and to fly. And so eventually that flight became full powered flight, and these birds were able to develop flight, all thanks to creatures like the Archaeopteryx, which lived in treetops and stuff. And actually, I'm going to show you an animal here. Let me grab it real quick. Now, this animal is the direct descendant of the Tyrannosaurus Rex. So I'm going to show it off here for you. It's extremely ferocious. This is the most ferocious creature. No, it's not that ferocious. It's a chicken. Chickens, believe it or not, are the direct descendant. Oh, hold on. Come here, Lacey. This is Lacey. She's our chicken. I have her on a leash right now, if you're wondering what that is, that harness is. But chickens, hold on. Chickens, hey, relax. Chickens are the direct descendants of Tyrannosaurus rexes. So we did some genetic data. We took the genetics of a Tyrannosaurus rex and we compared it to the genetics of a bunch of modern animals, and we found that chickens are the most similar to a T-Rex. So these guys are birds, and birds directly descended from dinosaurs. What happened was, whenever the dinosaurs were around, some dinosaurs, like the Archaeopteryx, for instance, slowly developed flight using feathers, and then modern-day birds are all descended from those guys. So chickens nowadays can't fly, but they can definitely get themselves up. They can actually lift themselves up to 30 feet in the air. They just can't keep themselves up there. So chickens have a lot of similar characteristics to dinosaurs. So, like, for instance, a lot of dinosaurs had hollow bones, and modern-day birds also have hollow bones. Oh, my goodness. You're not happy today, huh? So another thing that chickens have are talons. Now, their talons don't hurt or anything. They're not very sharp talons. But dinosaurs have feet very similar to this. In fact, these are the same kind of feet that you'll find on creatures like the Tyrannosaurus rex. It's just theirs are a lot bigger. These beaks, dinosaurs developed very rudimentary beaks that nowadays are much more specialized in modern animals. And even things like feathers originally began in dinosaurs as a way to regulate their body heat, to keep themselves warm. So we can actually look at the fossil record and very clearly trace how chickens descended from dinosaurs. Do you have any questions about chickens?
No.
Okay. Well, I'm going to put her back because she's not happy with me right now. She is just adorable, though I love chickens. But these guys are the closest living relative to the modern T-Rex. Oh my goodness. Okay, so real quick here, we're gonna just touch on a few more things here. I wanted to give an example of a creature that survived several mass extinctions. The trilobite. There's this little guy here. I have a fossil of a trilobite, but here's a much better image of a trilobite here. They managed to survive for nearly 300 million years. And at one point were roughly 1/3 of all the species on the planet. So 1 out of every 3 creatures was a trilobite at one point. But they went extinct completely. And so we actually use them nowadays. If we find, because of how common they were, if you find a trilobite, you're able to safely say that something is older than 250 million years whenever you find things like trilobites. So extinction events help us to define periods in geologic time. Another example of strange geology is the evolution of whales. So whales began as ungulates, so related to hippos, deer, horses, things like that. And then over time, the ancestors to modern hippos slowly spent more and more time in the water until eventually they were completely and totally water dwelling. So you get things like dolphins and whales, all because some creatures that were kind of similar to a hippo or a cow once upon a time spent more and more time in the water. And then you also get things like giant ground sloths. So once upon a time, there were a couple different kinds of sloth. One of them was the giant ground sloth, which was like the size of a bear. It was huge, it was massive, and but the problem was it was in competition with so many other creatures that it went extinct. Whereas the modern day two-toed and three-toed sloth, nothing hunts them because they are basically they have no nutritional value, so creatures don't even hunt them down because they don't really have a whole lot going on. They're not a good food item, and so nothing competes. And also, they barely get by, so nothing competes with them. So it's kind of interesting to see. Whenever we talk about evolution and creatures, I think we tend to think that creatures evolve to become extremely strong or powerful or whatever. The simple truth of the matter is they don't. They actually just sort of slowly become whatever is the most successful. And in this case, a two-toed or a three-toed sloth was more successful than a giant ground sloth, even though the giant ground sloth could very easily take a modern day sloth in a fight. You know, like these guys were big, massive, terrifying creatures, but unfortunately, they just didn't have what it takes to survive. So we study extinction events to help us understand where we came from, what is driving change in ecosystems, and to give us a little bit more perspective, because we are actually powerful enough to cause extinction events. In fact, right now, we are driving a 6th mass extinction. So creatures are dying at an incredibly fast rate. And it's only through great effort on our part that we can slow it down or stop it. So that is all I have. Do you have any questions about extinction?
No.
Okay, cool. Well, I hope you have a good day, and I will see you later. Bye.